Usually, when a massive industrial enterprise bleeds capital, there is a very legible paper trail, right? Like you can pull up an enterprise resource planning dashboard or look at the supply chain logistics and, point to a specific bottleneck in a spreadsheet.
Yeah, you can identify exactly where the margins are evaporating. It's usually pretty black and white.
Exactly. But when you step onto the floor of a modern steel melt shop, specifically, like into the operational radius of an electric arc furnace, that financial bleed, it totally defies standard accounting.
It really does. It's not sitting on a spreadsheet.
No, it's literally vanishing into thin air. It's burning up in a contained 3,000-degree lightning storm.
And, the scale of that invisible waste, it's actually quite difficult to conceptualize until you really look at the raw thermodynamics involved.
Right.
I mean, we are talking about a process that consumes tens of megawatts of continuous electrical power just to melt a highly variable mixture of scrap metal.
And to ground this in hard numbers for you, the listener, we've pulled together an incredibly dense stack of source material for this deep dive.
Yes, some really fascinating papers.
We're going to be dissecting the AI's Tech 2021 research on electrode consumption best practices, which was led by Bipin Richararya. We're also pulling from Dr. Ben Bowman's foundational work on the physics constraints of graphite ware,
which is absolutely crucial to understanding this.
Right. And we're looking at hardware architecture specs from AMI Automation's IOTrode systems. Plus, we're framing all of this through a really interesting philosophical white paper called The Quiet Architect.
That one focuses on the human safety element, right? Restorative engineering.
Exactly. The whole mission of this deep dive is to understand this incredible transition from blind, reactive industrial operation to, well, total predictive awareness.
And the baseline financial stakes outlined in those sources, they really set the stage perfectly.
So walk us through those numbers.
So an electric arc furnace, or EAF, missing its best-in-class energy target by a mere 80 kilowatt hours per ton, which doesn't sound like much, translates to a completely unrecoverable $2.8 million a year for a standard high-capacity plant.
Wow, $2.8 million.
And that is strictly the utility bill. That's just the electricity.
And the compounding factors are where the margins really collapse, right? Because beyond the electricity, you have like $3 to $5 million a year in electrode overconsumption.
Right, the graphite just burning away.
Yeah. And then you have the silent, totally unmeasured 2 to 4% loss of your actual metallic yield.
The liquid steel itself.
Exactly, just getting trapped in the slag layer every single shift. And then downstream, you have the off-spec heats that fail chemical analysis and require costly reprocessing.
It adds up fast.
It really does. When you aggregate all of that, you are looking at an operational leak that can define whether a facility remains globally competitive.
Absolutely. And the root cause of that leak, it fundamentally comes down to the discrepancy between the inputs and the control systems.
Break that down a bit.
Well, you have an incredibly dynamic, heterogeneous input. Every single bucket of scrap charged into that furnace has a completely different density.
Right, different moisture content, different chemical makeup.
Exactly. Yet, historically, the control systems applied to process that dynamic input have been completely rigid. They run these static power profiles.
Right, so the operator throws a highly unpredictable variable into the crucible, and the machine responds with a predetermined, fixed recipe.
Yeah, a recipe that just assumes average conditions, which of course is almost never the reality.
So over the next hour, we are going to explore how artificial intelligence and predictive data models are actively dismantling those static recipes.
We're looking at machine learning architectures that actually predict energy requirements in real time.
Yeah, and the use of acoustic proxy signals to measure the immeasurable, right? And the edge computing hardware that translates all this deep learning into the physical actuation of multi-ton hydraulics.
It's incredible tech. But to really grasp the mechanical elegance of those solutions, we first have to analyze the anatomy of the waste itself.
Right, where is the money actually burning up?
Exactly. The Bipin Richararya study breaks the EAF operational cycle down. And if we look closely at the distinct phases of a single heat, the systemic vulnerabilities become very obvious.
Let's walk through the thermodynamics of those phases, starting with the initial charge. So when the roof of the furnace swings back shut and the electrodes descend into the cold scrap, you enter the boring and penetration phase.
Right. And the metallurgical goal here is to establish the initial melt pools at the very base of the furnace.
And to achieve that, the transformer pushes maximum current at a moderate voltage.
The energy intensity of that initial, say, 8 to 12 minute window is just staggering. It utilizes roughly 30 to 35% of the total electrical energy allocated for the entire batch.
Just in the first 10 minutes.
Yeah. And the vulnerability here stems from the physical obstruction of the scrap itself. The operator is fundamentally blind.
Because the scrap pile completely obscures the progress of the electrodes.
Precisely. Making it impossible to visually or even thermally confirm when that melt pool has been sufficiently established.
It's honestly crazy to think about. You are operating a 100 megawatt machine based on a stopwatch.
Basically, yeah.
Because they cannot verify the bore depth, the standard operating procedure is just to let the timer run out on the initial power profile.
Which means the furnace is frequently blasting peak current into a melt pool that has already reached optimal liquid volume.
Right, expending massive amounts of energy with zero metallurgical benefit. It's like trying to cook a highly complex stew in a pitch-black room.
That's a great analogy.
You know, using ingredients of totally unknown sizes, and you're relying entirely on a kitchen timer instead of just being able to check the pot.
And when that timer finally goes off, which forces the transition into the meltdown phase, the surrounding scrap begins to collapse into the newly formed liquid bath.
So the electrical parameters have to shift.
Right. Voltage increases to lengthen the arc, providing the necessary radiant heat to liquefy the remaining solid mass.
And this phase, this 15 to 25-minute phase, is dominated by the strategic timing of the second or third scrap bucket charge.
And the margin for error on that timing is incredibly narrow.
Explain why that is.
Well, if you drop the subsequent charge too early, you end up mechanically burying the electrodes in this semi-solid material, which risks a major electrode breakage.
Which is catastrophic.
Yeah. But if you hold off and wait too long, the arc is just radiating extreme thermal energy into an increasingly empty upper furnace.
Right, which damages the water-cooled panels and burns through electricity at an agonizing rate.
And again, the operator is forced to make that call, relying on indirect visual cues and lagging thermal indicators.
Still somewhat blind.
Exactly. Now, once that final bucket is melted, the system shifts into the refining and flat bath phase. The scrap is entirely liquid, the surface is flat, and the sole objective is to superheat the bath to the precise tapping temperature required by the ladle furnace downstream.
The economic penalty of time in that flat bath phase is brutal. I was looking at the energy dissipation rates, and every single extraneous minute spent superheating the steel burns through $40 to $60 in pure energy and electrode wear.
Just poof, gone.
Right. You aren't altering the chemistry, you aren't adding yield, you're just paying to keep the system hot.
And that superheating process leads directly into the final phase, the tapping phase. The eccentric bottom tap opens, and the steel pours into the ladle.
And the temperature tolerance here is punishing, isn't it?
Unbelievably so. An overshoot of a mere 10 degrees Celsius at tapping, which is a microscopic margin of error when handling 1600-degree liquid metal.
Right, 10 degrees out of 1600.
Yeah, that cumulatively wastes over $200,000 annually in an average melt shop, while simultaneously degrading the refractory lining of the receiving ladle.
So across all four phases, the initial boring, the meltdown, the flat bath, and the tapping, the common denominator of the waste is this lack of real-time visibility.
It's all about flying blind.
Right. And it begs the obvious engineering question. If you are losing literally millions of dollars because you can't see the state of the melt, why not just introduce direct telemetry? Put a sensor in there.
Well, the environment inside the EAF crucible is uniquely hostile to direct instrumentation. I mean, it goes far beyond just the ambient temperature.
The heat is one thing, but there's more to it.
Much more. The electric arc generating the heat creates an extreme state of electromagnetic interference, or EMI. It is a localized, sustained electromagnetic storm.
I was reading through the sensor failure analysis in the sources, and it's fascinating how quickly standard industrial telemetry just degrades in there.
It doesn't stand a chance.
It isn't just a matter of heat shielding, right? Like, even if you encase a thermocouple or an optical sensor in advanced ceramics, the EMI fundamentally corrupts the data transmission anyway.
Yeah, the electrical noise floor is so incredibly high that the signal-to-noise ratio renders the telemetry completely useless within minutes.
Long before the physical probe even blisters and warps from the thermal shock.
Because you are dealing with intense magnetic fields generated by currents exceeding 50,000 amps.
50,000 amps.
Any standard analog or digital signal originating from within that field is going to be entirely swamped.
It's the equivalent of trying to have an A nuanced, whispered conversation while standing directly next to a jet engine at takeoff?
It's exactly what it's like.
Right. No matter how sensitive your microphone is, the sheer volume of the interference makes data extraction totally impossible. So you end up relying on a kitchen timer to orchestrate one of the most volatile physical processes in heavy industry.
And the realization that direct internal measurement is physically impossible, it forces a complete pivot in the engineering approach.
Right. If you can't put a sensor in the storm.
Right. If the primary environment actively destroys the instrumentation, the solution is not to build a tougher instrument. The solution is to identify and measure a secondary emission that actually escapes the primary environment intact.
So if you cannot survive the lightning, you basically have to find a way to listen to the thunder.
I love that phrasing. And that brings us right to the acoustic proxy method, which is just one of the most elegant applications of signal processing in modern metallurgy.
Let's get into this because the focus here is mitigating the physical wear on the graphite electrodes, right?
Yes. Rather than attempting to visually monitor the degradation of the electrode tip inside the crucible, engineers developed a system that relies entirely on high-frequency acoustic analysis.
Let's break down the physical architecture of that acoustic system because, honestly, the installation constraints alone are just fascinating.
They really are.
They utilize a heavy, milled aluminum acoustic sensor array, but they don't place it anywhere near the active heat zone.
No, they mount it heavily shielded, positioned way back behind a dense concrete blast wall on the factory floor.
Which seems wild to me.
Well, the concrete barrier serves a dual purpose. Obviously, it protects the sensor hardware from the physical hazards of the melt shop, slag splashing, radiant heat, accidental impact.
Standard protection.
But more importantly, it acts as a passive low-frequency acoustic filter.
Okay.
The low-frequency rumble of the factory, all the cranes, the mechanical vibration, it really struggles to penetrate the density of the concrete.
Okay, I am looking at this from the perspective of, say, an electrical engineer, and the skepticism is immediate.
Oh, for sure.
A microphone hidden behind a massive concrete wall in one of the loudest industrial environments on planet Earth is somehow expected to dictate the precise position of a massive hydraulic mast.
Sounds impossible.
Like, how do you possibly isolate the specific sound of the electric arc from the ambient noise of a crane dropping 50 tons of scrap metal just 20 yards away?
Right, well, the isolation is achieved through fast Fourier transforms, or FFTs.
Okay, unpack that for us.
So the sensor isn't simply recording raw audio volume. It's not just checking how loud it is. The acoustic array captures the time domain audio signal and feeds it into edge computing processors that execute these FFT algorithms in real time.
And what does the FFT actually do to the sound?
It essentially converts the audio from a continuous waveform over time into a spectrum of specific isolated frequencies.
So they are slicing the audio apart to look at the pitch rather than the volume.
Precisely. The ambient noise of the factory, the cranes, the hydraulic pumps, all the clanging operates on lower frequency bands.
Bass notes, basically.
Exactly. The electric arc, however, generates highly distinct high-frequency acoustic signatures. Furthermore, the frequency of the arc actually shifts dynamically based on the physical environment inside the furnace.
Oh, wow. So the acoustic profile changes as the scrap melts down or as the phony slag layer builds up, and crucially, as the physical length of the graphite electrode degrades. Exactly. Because the physics of the arc dictate the sound. A long arc striking cold, jagged scrap produces a distinctly different high-frequency signature than a short arc striking a flat, liquid bath covered in slag.
That makes a lot of sense.
So engineers spent months recording these dense acoustic profiles, heat after heat. And once the furnace was powered down between heats, they physically measured the remaining length of the graphite electrodes using manual calipers.
They mapped the telemetry. They fed the high-frequency acoustic shifts into a deep learning model, aligning the sound data with the physical caliper measurements.
Yes, they trained the neural network to understand that when the frequency spectrum looks exactly like this, the electrode has degraded by exactly that many millimeters.
That is brilliant. They established a baseline predictive wear model, but the real breakthrough occurs when that model transitions from passive monitoring to active control, right?
Exactly. Because the legacy systems utilize reactive impedance control, which attempts to measure the electrical resistance of the circuit to determine how far the hydraulic mass should lower the electrode.
But as we established earlier, that electrical data is constantly subjected to massive EMI. So the impedance readings are noisy, they're erratic, and they inherently lag behind the physical reality of the furnace.
Right. But the acoustic signal traveling through the air and passing through the concrete remains completely immune to that electromagnetic interference.
It's totally insulated from the storm.
Yes. So once the AI is trained, it ingests the FFT frequency data and actively dictates the proportional valves of the hydraulic mast. The edge computing architecture processes the audio and outputs a physical control signal in under 20 milliseconds.
20 milliseconds. So it effectively bypasses the electrical noise entirely.
Entirely.
The sound of the arc is directly driving the hydraulics, allowing the system to stabilize the arc length proactively. It reacts to the acoustic shift before the traditional impedance sensors even register a fluctuation.
And the stabilization of that arc translates directly to the preservation of the graphite, which introduces the budget gravity outlined in the Bipin-Ricarius study.
Let's talk about the graphite budget. Because graphite electrodes are not just some marginal consumable, right? They are one of the most severe line item costs in the entire conversion process.
Oh, easily. The study confirms that electrodes account for 10 to 20% of total EAF conversion costs.
10 to 20%.
Yeah. And the manufacturing process for industrial graphite is incredibly resource intensive. It requires months of baking petroleum coke at extreme temperatures. So a high-capacity furnace will consume between 1.5 and 3.0 kilograms of graphite for every single ton of steel produced.
So in a facility producing 1 million tons annually, the baseline expenditure for electrodes alone sits between $3 and $5 million.
It's massive.
Yeah.
So slashing that consumption rate is a paramount operational directive.
And the AI achieves this reduction primarily through dynamic arc control, completely abandoning those static power recipes we talked about earlier.
Right. The mechanics of how arc length dictates electrode wear are deeply tied to the physical state of the scrap.
Walk us through that physics.
So during the initial boring phase, the electrodes are surrounded by unmelted, cold scrap. That physical mass acts as a thermal shield, protecting the water-cooled sidewalls of the furnace from the radiant energy of the arc.
Okay, so the scrap is basically acting as a physical barrier.
Exactly. Recognizing the presence of that protective scrap shield, utilizing the acoustic proxy data, the AI model commands the transformer to push higher voltages, resulting in a longer, more powerful arc.
It aggressively maximizes power input because the geometry of the furnace allows it without risking structural damage to the sidewalls.
But the moment that scrap collapses into the liquid bath, that physical shield vanishes.
Right. The flat bath phase exposes the sidewalls directly to the arc.
And if the system were to maintain that long arc during the flat bath phase, the isotropic radiation of the plasma would severely damage the refractory lining, and it would accelerate the degradation of the electrode itself due to excessive exposure.
So it has to adapt.
Fast. Therefore, the AI dynamically drops the voltage and increases the current, actively shortening the physical length of the arc.
It focuses the thermal energy directly downward into the liquid steel rather than allowing it to radiate outward. It operates very similarly to the logic of an automated blowtorch.
That's a really good way to visualize it.
Like, if the flame is striking a dense block of ice, the system widens the aperture, blasting maximum heat because the ice absorbs the energy safely. But the millisecond that ice melts into a shallow puddle,
Right.
the system constricts the flame to a tight pinpoint focus. It maintains the localized temperature while preventing the backsplash of radiant heat from, melting the nozzle itself.
That's spot on. And by continuously adapting the arc length to the precise state of the melt, the AI limits the exposure of the graphite, yielding an 8 to 15% reduction in overall electrode wear.
Which is huge.
And concurrently, because the thermal energy is directed efficiently into the steel rather than radiating into empty space, the dynamic power profiling saves between 30 and 60 kilowatt hours of electrical energy per ton.
So going back to our initial baseline from the intro, closing just an 80 kilowatt hour gap saves $2.8 million.
Right. The dynamic arc control alone captures the vast majority of that electrical waste, while simultaneously pulling hundreds of thousands of dollars out of the consumable graphite budget.
It's a double win. But the complexity deepens even further when we analyze the specific physics constraints governing that graphite loss.
Right, Dr. Ben Bowman's research. He isolates the wear into two distinct mechanisms, tip sublimation and sidewall oxidation.
Let's take those one by one.
So I read Dr. Bowman's paper on the tip sublimation process, and he frames it almost as an unavoidable consequence of the physics. Like, the core of the plasma arc reaches temperatures exceeding 5,000 degrees Celsius, right?
Yes, incredibly hot.
while the sublimation point of graphite, which is the temperature where it transitions directly from a solid to a gas, is around 3,600 degrees.
So it's way hotter than the vaporization point.
Exactly. If the physics dictate that the arc is fundamentally hotter than the vaporization point of the material, how does software possibly intervene? I mean, no algorithm can alter the laws of thermodynamics. You are hitting on the absolute core constraint. You're right, the AI cannot change the melting point of carbon. However, the total mass lost to vaporization is a function of both temperature and the duration of peak current density.
Ah, duration.
Yes, the dynamic arc control algorithms restrict the duration of that peak current density to the absolute mathematical minimum required to maintain the melt. It minimizes the time the tip spends in that critical sublimation zone.
Okay, so it mitigates the vaporization through time management, essentially.
Precisely. Now, the second mechanism, sidewall oxidation, requires a completely different intervention.
Explain sidewall oxidation for us.
So as the red-hot body of the electrode is exposed to the oxygen-rich atmosphere of the upper furnace, the carbon physically reacts with the oxygen and burns away. It tapers the cylinder over time until the structural integrity fails and the electrode snaps.
Just structurally weakens it. And to combat that oxidation, the hardware integration becomes critical, right? We looked at the specifications for AMI Automation's IOSROAD module. It utilizes high-definition optical cameras and computer vision classification models to visually track the degradation.
Which is crazy because the immediate logistical challenge is positioning a camera near a 3,000-degree furnace.
Right. How do you keep the lens from melting?
Well, the iTrode system does not look inside the crucible. The optical hardware utilizes extreme telephoto lenses to monitor the upper sections of the electrode columns that remain outside the immediate heat zone.
Oh, that makes sense.
Or it analyzes the geometry of the tip during the brief moments the mast is fully retracted between heats.
I see. So the edge detection algorithms map the physical geometry of the cylinder, calculating the exact rate of tapering caused by the oxidation in real time.
Yes, and it merges that visual classification data with the acoustic proxy models we discussed and the real-time thermal telemetry.
It's all feeding into the same brain.
Exactly. Once the AI calculates the precise rate of oxidation, it actively intervenes by controlling the electrode water cooling rings.
So literal water flowed down the sides of the graphite.
Yes, and it is an incredibly delicate thermodynamic balancing act. The AI adjusts the hydraulic valves to flow just enough water down the surface of the electrode to drop the surface temperature below the critical oxidation threshold.
But if it overcools the electrode, that water enters the furnace atmosphere, absorbing thermal energy from the melt and driving up the electricity bill.
Exactly. The software is constantly walking this tightrope between cooling the consumable and chilling the furnace.
That is fascinating. The continuous adjustments to the water rings combined with the dynamic arc length create a really comprehensive defense against both sublimation and oxidation.
They do. However, the Bipin-Racharia study emphasizes that even with advanced AI, the physical realities of the charge mix constantly threaten the optimization models.
Right, you can't control what scrap metal you're buying.
Exactly. The study spends significant time discussing the conductivity variables of the scrap. If a plant charges a bucket of highly dense, conductive, busheling-like heavy industrial offcuts, the electrical pathway is strong, the impedance is low, and the arc stabilizes quickly.
Easy mode for the AI.
Contrast that with a charge of low-grade, rusty, shredded municipal scrap. The heavy oxidation layer on the rusty scrap acts as an insulator.
Oh, so the electrical resistance spikes.
The resistance spikes, the arc becomes erratic, and the AI must work exponentially harder to maintain the power profile.
And the Racharia team encapsulates all these variables into what they call a severity factor, right?
Yes, the severity factor. It's a quantifiable metric representing the inherent oxidizing environment of the specific furnace.
What goes into that metric?
It incorporates the draft capacity of the exhaust systems, the efficiency of the manual oxygen lancing, the baseline quality of the local scrap supply, and even the physical dimensions of the crucible.
It is basically the operational fingerprint of the machine.
Exactly. So the AI cannot simply be installed with a generic model. It must undergo a machine learning training period to understand the unique severity factor of the specific hardware it is controlling.
The system literally has to learn the personality of the furnace.
That's a great way to put it. But, the most profound insight regarding these control systems is that optimizing the electric arc furnace in isolation is frequently counterproductive to the overall facility.
Right, because the EAF is merely the first step.
Yep.
The symbiosis between the primary melting furnace and the subsequent secondary metallurgy, specifically the ladle furnace, or LF, is where the real complexity lies.
Absolutely. The liquid steel must flow from the EAF into the LF for final chemical refining.
And the operational state of the EAF totally dictates the baseline workload of the ladle furnace. They are thermally and chemically interlocked.
Let's map out a failure of that symbiosis just to show the stakes. Let's assume the EAF operator, utilizing legacy control systems, taps the liquid steel into the ladle at 1,585 degrees Celsius, when the strict target required by the ladle furnace is 1,600 degrees.
So they are 15 degrees short.
Right. A 15-degree deficit in a massive volume of steel forces the ladle furnace to act as a primary heater rather than a chemical refiner.
Which is not its job.
Not at all. The LF operators must lower their own electrodes and apply intense electrical power to raise the temperature of the bath before they can even begin the alloying process.
And that 15-degree shortfall adds, what, 10 to 15 minutes of unplanned processing time at the LF station?
Easily, it consumes excessive electricity and causes a massive logistical bottleneck for the continuous casting machines waiting downstream.
So the EAF might have saved 2 minutes by tapping early, but it created a 15-minute delay for the entire rest of the plant.
Exactly. And the reverse scenario is equally destructive. If the EAF overheats the steel to 1,615 degrees, attempting to provide a thermal buffer.
Right, just to be safe.
Yeah, that excess thermal energy violently attacks the magnesia-carbon refractory bricks lining the ladle. The chemical binder in the bricks degrades, forcing premature replacement of the ladle lining.
Which is an agonizingly expensive maintenance procedure.
Very expensive.
So if the penalty for misalignment between these two machines is so severe, why did the industry tolerate siloed control systems for decades? Like, the EAF operator had their screens and KPIs, and the LF operator had theirs.
Well, the human element naturally leads to local optimization rather than systemic optimization.
Yeah.
A human operator, even a highly experienced one, cannot mentally calculate the multivariable thermodynamics required to predict the exact temperature drop of the steel as it is poured through the ambient air, splashes into the ladle, and waits for transport.
Right, the math is just too dense.
Way too dense for a human on the fly.
And to bridge that gap, the predictive models utilize LSTM architectures, right? Long short-term memory neural networks.
Yes, LSTMs are perfect for this. Standard feed-forward neural networks struggle with time series data because they process inputs independently.
They don't remember the past sequence.
Right. An LSTM network contains memory cells that allow it to retain relevant information from earlier in the sequence, making it exceptionally powerful for predicting continuous thermodynamic processes.
So the LSTM continuously ingests the real-time electrical telemetry, acoustic data, and chemical analysis from the EAF. It factors in the ambient temperature of the plant floor and even the specific thermal history of the ladle being used.
And it crunches all those variables to predict the final arrival temperature of the steel at the ladle furnace.
The performance metrics on those LSTM models and the sources are just incredible. The data indicates they can hit the ladle furnace endpoint temperature targets within a margin of plus or minus 5 degrees Celsius with 89% accuracy.
Which is a game changer. Eliminating that thermal variance stabilizes the entire secondary metallurgy process. When the LF operator knows with 89% certainty the exact thermal state of the incoming steel, the scheduling bottlenecks just evaporate.
The ladle furnace operates purely as a refiner, which is its intended purpose.
Exactly.
And the stabilization of the ladle furnace provides the foundation to attack the next massive vector of waste, metallic yield.
Right, the actual steel itself.
Yeah. The source data highlighted a silent 2 to 4% loss of yield to the slag layer. Over 1 million tons of production, losing 3% of your primary product is catastrophic.
The yield loss frequently occurs during the chemistry trimming and desulfurization phase at the LF. The crude steel arriving from the EAF lacks the precise elemental composition required for specific commercial grades.
It is essentially a blank canvas.
Right. To create high-tensile rebar or automotive-grade sheet metal, the LF operators must inject highly specific ferroalloys like vanadium, manganese, silicon, aluminum into the liquid bath.
And those ferroalloys are extremely premium commodities.
Very expensive. In a legacy system, the operator extracts a physical sample of the steel, sends it via pneumatic tube to the mass spectrometry lab, and then waits for the chemical breakdown.
Old school.
Yeah. And once the baseline chemistry is known, the operator relies on static tables or manual calculations to determine the necessary alloy additions.
And this is where the human psychological element heavily influences those manual calculations, isn't it?
Well, entirely. Because the cost of failing a final specification check is so high, requiring the entire batch to be reprocessed, destroying the plant schedule operators, inherently build massive safety margins into their math.
Just to cover their bases.
Exactly. If the metallurgical specification demands a minimum of 1.0% manganese, the manual calculation will frequently aim for 1.15%. The operator systematically overalloys the steel to guarantee compliance.
They inject expensive insurance into every single heat. That systematic overalloying drains between $5 and $15 per ton directly from the profit margin.
It's a huge leak. And to eradicate that human safety margin, the AI models deploy genetic algorithms.
Let's get into this because a genetic algorithm is a search heuristic inspired by the principles of natural selection and evolutionary biology, right?
That's correct.
Let's break down the mechanics of a genetic algorithm in this specific context. How does evolutionary math dictate the injection of vanadium?
It's fascinating. The algorithm begins by generating a massive initial population of potential alloy recipes. It takes the real-time spectrometer data of the crude seal and the target specification for the final grade. It then evaluates each generated recipe against a strict fitness function.
Okay, so the fitness function defines the goal. In this case, the fitness function requires the recipe to hit the exact chemical specification while utilizing the absolute minimum volume of expensive alloys.
Right. The algorithm discards the recipes that fail the fitness function. The ones that miss the spec or cost too much, it just kills them off.
Survival of the fittest.
Literally. It then takes the surviving high-performing recipes and applies crossover and mutation functions. It mathematically breeds the best solutions together, introducing slight random mutations to avoid getting trapped in local optima, and then evaluates the new generation.
And it runs thousands of these evolutionary generations in milliseconds.
Yes. It simulates the chemical reactions of countless combinations until it isolates the apex recipe, the mathematical absolute minimum dosage required to hit the grade.
By replacing manual safety margins with evolutionary mathematics, the genetic algorithms consistently reduce total plant-wide alloy consumption by 12 to 18%.
It's just staggering efficiency.
It is the mathematical equivalent of a master baker scaling a recipe for a massive industrial vat of dough. Instead of a human throwing in an extra handful of salt just to be safe, the AI calculates the exact molecular requirements and realizes the batch needs precisely 3 additional grains of salt to achieve the perfect profile.
The yield is protected, and the ingredient waste drops to 0.
But the preservation of the yield extends beyond just the alloy chemistry, right? It also relies on fluid dynamics, specifically adaptive argon flow control.
Yes, the stirring process.
Explain the plumbing of the ladle furnace for us. Why are they injecting argon gas into the bottom of the liquid steel?
Well, argon is an inert gas, meaning it will not react chemically with the steel. It is injected through porous plugs in the bottom of the ladle to physically stir the liquid bath.
So the gas bubbles rise through the liquid, homogenizing the temperature and mixing those injected ferroalloys.
Crucially, the argon plume relies on Stokes' law to clean the steel. As the bubbles rise, they capture microscopic non-metallic impurities, known as inclusions, and float them up to the surface, where they are absorbed and trapped by the slag layer.
It acts like a scrubbing mechanism.
Basically, yeah. The physical dynamics of that stirring process present another massive vulnerability. If the operator sets the argon flow rate too low, the fluid velocity is insufficient to float the inclusions.
Right. The impurities remain suspended in the steel, the batch fails the quality audit, and the material must be downgraded or scrapped.
However, if the operator pushes the argon pressure too high, attempting to aggressively clean the bath,
The violent turbulence on the surface ruptures the protective slag blanket, doesn't it?
it does, and the liquid steel is suddenly exposed directly to the atmospheric oxygen.
The steel reoxidizes, the premium alloys you just injected burn away, and the metallic yield literally goes up in smoke. It's a razor-thin operational window governed by the specific chemistry of the slag.
And the optimal stirring intensity is entirely dependent on the viscosity and composition of that slag layer. But real-time chemical analysis of slag is notoriously difficult. The lab results lag far behind the speed of the process.
Which is where the AI comes back in. It circumvents the lab delay by utilizing predictive modeling. It aggregates the initial EAF chemistry data, the thermal telemetry, and the real-time optical data from the ladle surface to estimate the slag composition instantaneously.
Yes, and based on that continuous estimation, the system actively modulates the mass flow controllers on the argon gas lines.
It dynamically adapts the pressure and volume of the bubbles.
Exactly, maintaining the exact fluid velocity required to float the inclusions without breaking the surface tension of the slag.
It watches the invisible chemistry and actively rides the pressure curve, ensuring grade-compliant steel is produced consistently without triggering those disastrous 20-minute reprocessing delays.
It's all about avoiding those delays.
The cascading financial impact of all these models, the dynamic arc control, the acoustic proxy, the LSTM temperature predictions, the genetic alloy algorithms, the adaptive argon flow, it's just monumental. We are talking about reclaiming millions of dollars of lost capital per furnace per year.
The optimization of the balance sheet is undeniable. But, you know, focusing exclusively on the capital efficiencies completely ignores the most critical outcome of predictive architecture.
Which is?
The ultimate metric of success in heavy industry is not the profit margin. It is the physical safety of the human workforce.
And this transitions perfectly into the final source text, The Quiet Architect, which outlines the philosophy of restorative engineering.
Yes. The premise is that advanced technology should not be built merely to generate headlines about automation or efficiency. It must be deployed to actively absorb physical risk.
The application of predictive maintenance models embodies that philosophy entirely. The AI systems are continuously analyzing the acoustic signatures, the hydraulic pressures, and the thermal gradients of the machinery.
And because of that, they are capable of identifying the microscopic precursors to catastrophic failure days or even weeks before the failure actually occurs.
The data shows a reduction in unplanned downtime by 25 to 40%. And from a management perspective, sure, that stabilizes the production schedule. But let's look at what unplanned downtime actually means on the factory floor.
It's never a good situation.
It is rarely a gentle shutdown. Unplanned downtime in a melt shop is a violent, chaotic event.
It is an immediate crisis. If a water-cooled panel on the EAF develops a leak during a heat and water breaches the crucible and contacts the liquid steel.
The sudden expansion of steam creates a massive explosion risk.
Exactly. Or if a hydraulic line controlling the electrode mass ruptures, the machinery can literally crash.
And when those failures happen reactively, human maintenance crews are forced to rush into an incredibly hazardous zone.
The ambient heat is still lethal, the high-voltage systems are potentially compromised, and the pressure from management to get the line running again creates a really dangerous cognitive load.
They are operating in a state of reactive emergency. People make mistakes in emergencies.
But predictive maintenance completely neutralizes that emergency. Because the AI model identifies the degrading hydraulic seal or the thermal anomaly in the water panel well in advance, the repair becomes a scheduled event.
The furnace is powered down systematically, the heat is allowed to dissipate safely, the high-voltage systems are locked out,
And the maintenance technicians perform the physical repair in a controlled, deliberate environment.
The AI absorbs the chaotic variable. It steps into the electromagnetic storm, monitors the degradation, and issues the alert before the threshold of physical danger is ever crossed.
That is the very essence of restorative engineering.
It really is. We spend so much cultural energy discussing artificial intelligence as this existential threat to human employment, But when you look at its implementation in these extreme physical environments, it acts as the ultimate shield.
It really does. It allows the human operator to step back from the hazard zone and manage the complex systems from a position of strategic safety.
The technology restores the baseline expectation that a worker will return home unharmed.
It is a profound shift in the relationship between the operator and the machine. The AI manages the invisible high-speed physics, allowing the human to govern the overall process without relying on dangerous guesswork.
So, to pull the thread through everything we've discussed today, we analyze a massive industrial system that historically bled capital through rigid, reactive protocols. We examined the thermodynamic vulnerabilities of the EAF melting phases and how electromagnetic interference blinded the operators.
Right, the lightning storm. And we explored the ingenuity of measuring secondary emissions using fast Fourier transforms on acoustic signatures behind concrete walls to accurately model electrode wear and bypass the electrical noise floor entirely.
We detailed the hardware and software integrations combating graphite sublimation and oxidation, utilizing dynamic arc control and high-definition visual telemetry to manage those water cooling rings.
And we connected the EAF to the ladle furnace, illustrating how LSTM neural networks bridge the operational silos, predicting thermodynamics to align the entire plant schedule.
We highlighted the secondary metallurgy, where genetic algorithms basically eradicate the expensive human safety margins in alloy dosing, and adaptive argon flows protect the metallic yield from reoxidation.
And finally, we grounded the entire technological stack in the reality of the factory floor, where predictive maintenance models eliminate the violent chaos of unplanned failures, fundamentally protecting the maintenance crews.
It is just a brilliant example of decoding the invisible to master the physical world, and that leaves you with a final thought to consider as you step back into your own work. We just explored how finding the right proxy signal, listening to the acoustic thunder of an electric arc, can optimize one of the most violent manufacturing processes on Earth. So look at the blind spots in your own industry, whether it is a supply chain bottleneck, a complex chemical process, or a seemingly unpredictable mechanical failure. If the primary environment is too noisy or too hostile to measure directly, what is the secondary emission? What is the invisible proxy signal that you should be listening for?